Welcome to this session. Today we are going to discuss some of the problems of composition functions and invertible functions. So here in the last session we discussed about what is a composition of functions. Now we are going to discuss the theorems which are related on composition of functions. So the first theorem is f and g are any two functions which are defined from f is from a to b, g is from b to c. Then the following are true. If f and g are 1 to 1, then g of f is 1 to 1. G of f is 1 to 1, then f is 1 to 1. Third one is if f and g are onto, so g of f is onto. Next, fourth one, if g of f is onto, then g is onto. So now we are going to prove these four problems in different four problems we are going to prove. Now it is given f and g are both are 1 1. Now we have to prove g of f is 1 1. So to prove g of f is 1 1, we have to take any two elements. If they are not equal, yes, suppose a1, a2 if I am taking, which belongs to a, because g of f is defined from a to b, f is defined from a to b, and g is defined from b to c. G is defined from b to c. Now this is g of f. G of f is defined from a to c. Now we have to consider any two elements here. If I am taking a1, a2 belongs to a and a1 is not a2, then g of f a1 is not equals to g of f a2, or otherwise the images are equal, then naturally the pre-image under GOF are also equal, then g of f is 1 1. Now we are going to assume that we are going to consider any two elements here, a1, a2, and let us assume that their images are equal. So g of f a1 is equals to g of f a2. Now if I am going to take like this can be written as like this: g of f of a1 is equals to g of f of a2. And here g is 1 1, so the image is here. The image is f of a1, here f of a1 and here f of a2. So then they are equal to a1 to a2 because their images are equal. So this is equals to g of f of a1 is equals to f of a1, g of f of a2 is equals to f of a2. So since f is also 1 1, whenever their images are same, then the elements are also same. So because we are going to use here g is 1 1 and f is 1 1, both we are going to use, and we are going to consider g of f of a1 is equals to g of f of a2, and we are going to prove that a1 is equals to a2. So subsequently we can say that g of f is 1 to 1. G of f is 1 to 1. Next, another one is second one. If g of f is 1 to 1, then prove that f is 1 1. F is 1 1. So for proving the second one, so we have to prove f is 1 1. F is 1 1, and of course it is g of f is 1 1 is given. So we have to take any two elements. Let us consider f is from here to here. I am just taking two elements, a1, a2 belongs to a, and I am going to take f of a1 is equals to f of a2, and then finally we are going to prove that a1 is equals to a2. Then I can say that f is 1 1. F is 1 1. So for this is the way that we are going to prove. So I am just taking f of a1 is equals to f of a2. And here f of a1 and f of a2 which are located here in B, and of course g is a function. For each and every element it is having image. So G of f of a1 is exist, G of f of a2 is exist. So I am taking G of f of a1, G of f of a2 because this is a function from b to c. Then this can be written as G of f a1, G of f a2. So G of f is already given, it is 1, 1. So G of f a1 is equals to G of f a2 implies a1 is equals to a2. Which implies I am just taking f of a1 is equals to f of a2 and we proved that a1 is equals to a2. So we can say that f is 1, 1. F is 1, 1. So this is the second one proof. Now the third one is f is, if f and g are onto, then g of f is also onto. So f and g both are onto functions. That means for each and every element here, if I am considering under f there is a pre-image, and here if I am going to consider every element under g, it is having a pre-image. It is having a pre-image. Now we have to prove that under GOF, if I am going to consider any element, let us say small c belongs to C, then if it is having a pre-image under G of f, then we can say that this is onto. This is onto. So for that, we have to consider one element, let us say C belongs to C. And since it is given already, f and g both are onto functions. So we have to consider any b, if I am taking from B, then it is having a pre-image. It is having a pre-image. Let that under f. So f b is equals to f of b. And similarly, C, if I am consider in the set C, then it is having a pre-image under G because G is also onto. So G of B is equals to C. Now we have to prove that G of f of a, G of f of a is equals to G of f of a, and which is f of a is already, it is given as B, and G of B is already given as the C. So I can say that any element, if I am considering C belongs to C, then definitely it has one image, pre-image under G of f. So that pre-image is A. So we can say that G of f is onto. G of f is onto. Now the fourth one, see G of f is onto is given, and we have to prove that G is onto. G is onto. So for proving G is onto, then we have to use the G of f is ontoness. So for that, so this is nothing but it is given itself because this is G of f is onto. So G of f of a is equal to C. So we can say that f of a definitely it belongs to B. Definitely it belongs to B. And G is a function. Subsequently, this f of a is also an image. F of a is also an image under G. So that is equals to G of f of a is C. So C is I am taking here. So I am going to consider it is having a pre-image under G. That pre-image is f of a. So we can say that f is onto. F is onto. So this is the way that we are going to prove the theorem. First one is if f and g are onto, so g of f is onto. If g of f is 1, 1, g of f is 1, 1, then f is 1, 1. If f and g are onto, so g of f is also onto. If g of f is onto, then g is also onto. Now let us consider the another theorem. So here f is a function from a to b, g is a function from b to c, h is a function from c to d. Then we have to prove this. That is the composition of functions. Satisfies associative law. So here, first of all, whether this is a function which is defined from which set to which set, and this is a function which is defined from which set to which set. That we have to define, and after that only we are going to prove the associativeness of these two. So it is given already. A is from, f is from A to B. F is from. And next G is from B to C. and H is from C to D. H is from C to D. Then I am just considering this is nothing but H circle G, H of G, H of G. And if I am going to consider this from here to here, then this is H of G of F, of F. Otherwise, this is nothing but H of G of F. This is S. And now G of F, if I am going to consider these two, if I am just taking these two, this is nothing but G of F. These two, the composition of F and G, we are representing G of F, which is from A to C, and H of G of F, H of G of F, which is from, this is nothing but H of G of F, which is from A to D. So either we have to consider this is from set A to D, or else if you are going to consider this is another function which is also defined from A to D. So instead of proving these two are equal, first of all we have to prove whether these two functions from which set to which set. So these two functions are defined from the same set A to D, from the same set A to D. Now we have to verify whether they are equal or not, whether they are equal or not. So here both are from A to D only, so I am going to consider one element in A, set A, x belongs to A. Now I am going to take it as the function of x. So this is nothing but h of g of f of x. And f of x is a function from A to B. So then this is f of x is equal to x image. I am going to take it as y. I am going to consider it as y. So I am just taking it as this is y. Now this is h of g of y. So I am going to write like this. And next g is also a function from B to C. Then I am going to take this as z, the image I am just considering as z. So I am going to get this as h of z. H of z. Where h of z will be? H of z will be, this is there in the set D. Now let us consider the another one. So in the same way we are going to prove this. So h of g of f of x, and f of x is equals to y. So g of y I am getting, and next g of y is equals to z. So I am going to get h of z. The image h of z. So under these both functions will be the same. So we can say that both are equal to each other. Both are equal to each other. This is true for every x belongs to A. For every x belongs to A. So in order to prove this theorem, the associatedness of three functions, that is nothing but the product of three functions or composition of three functions satisfying associative principle. To prove that, we have to first of all verify whether the two functions are defined from same set to same set, from where it is going to be, what is domain and what is codomain. We have to verify. After that, we have to verify the equality. So this is regarding this. And now another one is invertible function. Invertible function. A function f from A to B is said to be invertible. Is said to be invertible if there exists another function, g from B to A such that g of f is equals to identity, and next f of g is equals to the identity function. The identity function. That means if we multiply, f is said to be invertible if g of f is equals to I identity function and f of g is equals to identity function. Here g of f, why I am saying this is identity function defined on the set A. Defined on the set A. Here it is f is given from A to B. F is from A to B, and next g is from B to A. G is from B to A. So we are going to consider g of f, which is defined from A to A only. which is defined from A to A. Suppose f of g, if I am considering, now this is f is from A to B, then this is f of g is defined from B to B. So here I am taking f of g is IB, that means a identity function defined on the set B. This is identity function defined on the set A. So if it is possible to construct another function which satisfies these two conditions, then we can say that one is g is the inverse of f, and we can write it as g is equals to f inverse. G is equals to f inverse. So whenever one function is said to be invertible, we have to construct another function where the function is defined from, if it is defined from A to B, then we have to consider another function from B to A, and the composition of two functions, f of g and g of f, is the identity function. Then we can say that one is the inverse of the other, or g is the inverse of f, and we are going to write this is like this, g is equals to f inverse. Now let us concentrate some of the examples. So here, first example, A is equals to 1, 2, 3, 4. Set is A set is given, f, g are functions are given, and it is defined from A to A only. F is a function defined from A to A, and g is a function defined from A to A. G is a function defined from A to A. So now we have to verify g of f is the identity mapping, or f of g are identity, both should be identity mapping. Then only one can say that one is the inverse of the other. So here it is having 1, 2, 3, 4. What is the identity function? So here, if I am taking g of f, if I am considering g of f of 1, if I am taking, then that should be equal to 1, and g of f of 2 is equals to, then I am going to get 2, g of f of 3 is equal to 3, and g of f of 4 is equal to 4. Then only we can say that g of f is identity function. In the same way, f of g also identity function. In the same way we can consider. So f of g of 1 is 1, f of g of 2 is 2, and f of g of 3 is 3, and f of g of 4 is equals to 4. So if this condition is satisfied, then only you can say that the product, the composition is the identity mapping. So for that, let us consider g of f of 1. First one is g of f of 1. So it is nothing but g of f of 1. G of f of 1. And what is given? F of 1 is equals to 4. It is given. So one image is 4. So I am going to take it as g of 4. This is f of 1 is 4. Now what is g of 4? 4 images. 4 image is 1. So it is 1. It is a 1. So this is nothing but g of f of 1 is 1. Of 1 is 1 I am getting. So which is nothing but the IA of 1. And similarly for the other one, g of f of 2. So it is g of f of 2. What about f of 2? F of 2 is equals to 1. So g of 1 I am getting. What is g of 1 is 2 I am taking. So this is 2. And similarly g of f of 3 is. G of f of 3 is. So it is g of f of 3. So f of 3 is what is given? 2. So g of 2. So g of 2 is what? G of 2 is 3. So then it is IA of 3. So now g of f of 4. So it is nothing but g of f of 4. F of 4 is 3. So g of 3. What about g of 3 is equals to 4. So I can say that g of f is the identity mapping, identity function defined on the set A. In the similar way, we can calculate f of g also. F of g also. Similar way, I can consider f of g of 1. So this is f of g of 1. What is g of 1 is 2. So it is f of 2. What is f of 2 is 1. So f of g of 1 is equals to 1. Similarly, f of g of 2. So this is nothing but f of g of 2. So this is f of, what is g of 2 is 3. So f of 3, what is f of 3 is 2. So like this, f of g of 3. Then it is f of g of 3. What is g of 3 is? G of 3 is 4. So this is f of 4. What is f of 4 is? F of 4 is 3. Like this. So similarly, f of g of 4. So it is nothing but f of g of 4. What about g of 4 is? G of 4 is 1. So f of 1. What about f of 1 is? 4. So I can say that f of g is the identity element. So if f of g and g of f are identity elements, then we can say that one function is the inverse of the other. F is inverse of g, or g is the inverse of f. G is the inverse of f. Now let us consider the another one. So here, consider a function. So f is like this, and f of x is given. G is a function defined, and g of x is given. Now prove that g is the inverse of f. G is the inverse of f. Similarly, we are going to consider g of f. So what is g of f of x? So g of f of x. So this is x. So this is g of f of x. What is f of x is given already? G of 2x plus 5. So what is g of x is given? 1 by 2. Then x minus 5. So 2x plus 5 minus 5. So this is. So now 5 get cancelled. Finally, I am going to get x. G of f is equals to x. Similarly, we are going to calculate in the same manner f of g of x. So it is nothing but f of g of x. So this is f of, what about g of x is? G of x is equals to then 1 by 2 and x plus 5. This is, and next which is equals to, f of x is equals to 2x plus 5. So 2 into x is 1 by 2, x plus 5, x, what about this, 2 into, x minus 5 will be there here, and then this is 5, and then plus 5. So these two get cancelled. Finally, I am going to get these two get cancelled. Finally, I am getting x. So which is this. So instead of proving one function is the inverse of other function, we have to verify f of g and g of f is equals to identity function. Then we can say that both are inverses of each other. Now this is the another way also we can say that when we say that the function is invertible. So if the function is 1, 1 and onto, 1, 1 and onto-ness, then the function is invertible. The function is invertible. In another way, already we discussed this, and so one function is said to be invertible if f is, the function f is 1, 1 as well as onto, then we can say that it is invertible. Then here it is two functions are another theorem. Two functions are invertible functions are given. Then we are going to prove that g of f is also invertible, and we have to verify g of f is equals to this. G of f is equals to this. This we have to verify. Now, it is given already f and g are invertible functions. So, both f and g are 1, 1 and onto. Because of the a function is said to be invertible if it is 1, 1 as well as onto. So here f and g both are invertible functions. So they are 1, 1 and onto. So consequently, g of f if I am taking, then it is also 1, 1 and onto. It is also 1, 1 onto. So we can say that g of f is invertible. By obviously you can say that this is invertible. Now this is an obvious result, and we have to prove this. We have to prove this. So instead of proving this, already we said that one function is when we say that invertible, whenever the composition of these two is equals to identity function. So I am just taking this is one function and this is another function. Okay, this is f and this is h I am just taking, and I am just applying a composition. Then I am just taking g of f, okay, and composition of, let us assume that this is h I am taking, h is equals to identity function, or else I am taking h g of f is the identity function. Then I can say that h is the inverse of g of f, or g of f is the inverse of h. Inverse of h. Then obviously we can get the result. We can get the result. So first of all, we are going to assume, we are going to take the f inverse circle g inverse is equals to h. We are just taking another function. Therefore, so we are considering what is f inverse. F inverse is nothing but, see here what we are saying that f inverse is a function. F is from a to b, then f inverse is from b to a, and g is from what is that, a to b to c, g inverse is from c to b, g inverse is from c to b. This is g inverse. So now this is f inverse circle g inverse. F inverse circle g inverse is from a to c, is from c to a, is from c to a. What about g inverse? What about g of f whole inverse? So here g of f whole inverse is, this is once again f is from a to b, and next g is from b to c, then this is g of f is from a to c, then g of f inverse is from c to a, So g of f inverse and this product both are from c to a, Then we are going to verify, the equality. We are going to verify the equalityness. So now let us consider h I am taking like this, then g of f of h. So h, as usual, we took same, and I am just considering that. And we know already matrix function composition, function product is satisfies associative law. So for that, I am just taking, instead of just considering these two as one. So here f circle f inverse, so which is a identity function, and g circle g composition of identity element is itself g. So g circle g inverse is nothing but the identity function. So now another one is, if I am going to reverse this, so h of g of f, So I can get in the same way, I am getting the another way I am getting the identity mapping. Then here g of f of h and f of g of f, both are getting identity functions. So we can say that one is the inverse of the other. So I can say that h g of f inverse is equals to h. So g of f inverse is equals to h. H is nothing but f inverse circle g inverse. So this is the theorem is proved. In this way, first for proving g of f whole inverse is f inverse circle g inverse, first of all they are going to define from the same one set to the same other set, and after that we are going to prove the equalityness. Now the another one is example. So here it is given, f is given and function value is given. find F inverse. Find F inverse. So we have to verify whether F is 1 1 onto 1 1 ontoness. So here for that we are just considering, let us take any two elements. So A from the set A. So x1, x2 belongs to A. I am just taking. If I am considering x1 is not equals to x2, if I am considering x1 is not equals to x2, subsequently f of x1 is just substitute in the place of x equals to x1. F of x1 is x1 power 4 plus 1. F of x2 is x2 to the power of 4 plus 1. x1 and x2 both are not equal. Obviously, f of x1 is not equal to f of x2. So, whenever x1 is not equal to x2. So, from this we can say that f is 1, 1. From this we can say that f is 1, 1. Then, so we can say that f is 1, 1. So, the ontoness, if you are going to prove, both are nothing but the real number system. Both are nothing but we are going to get the defined on the function R. So, now, it is ontoness is also, I am going to verify. See, I am going to consider one element, x, one element, x if I am going to consider. See here, f inverse is nothing but, let us say, f from A to B, I am considering one element, x. One element, x. If it is having a pre-image, that is nothing but just whatever the values, that is, what is that function value is given already. For all values of x belongs to B, then we are going to get f of x. We are going to get a different f of x. Or else, whatever the value that we are going to obtain, the corresponding x1 is also going to be getting from A. So this ontoness is also obviously because of the given function itself. So we can say that it is invertible. Now we are going to find out what about the f inverse. What is the f inverse? So I am going to consider first y is equal to f of x. So here it is, this is f of x. Then I am going to consider this is equals to y. This is equals to y. So the image. So y I am taking. So then from this I am going to calculate what is its pre-image. What is its pre-image? F inverse is from where to where? So from B to A. From B to A. So I have to consider one element in B. What is that element? What is that element? That element is a fourth root of this. So now it is nothing but just y is equal to f of x. So then this is y, and just to simplify, and I am going to calculate x. So whatever the value will be there, this is f inverse of y. So x is equals to f inverse of y. So f inverse of y is equals to the function. So this is the inverse of a function. Inverse of a function. Now let us consider another one. So here in the same way we can calculate. So find A inverse. So for different values of x1 and x2, f of x1 is different other than the f of x2. F of x1 is not equal to f of x2. So here no different images will have different elements will have different images. So if the images are different, then the elements are also different. So we can say that f is 1, 1. F is 1, 1. And of course it is a function from A to B. It is given. So for all the values, it is going to be exist because it is a denominator is also a constant one. So, so I am going to get the ontoness, and we are going to verify the f inverse. F inverse. So whenever the functions is given, obviously it is ontoness is verified unless for certain values, the denominator will be a function of x will be there. Then for such problems may not be exist in some cases. So here we are going to easily f is ontoness, because for every x this function is going to be exist, and that is its pre-image. That is its pre-image. Whatever the value that we are going to take from x, which is a real number, which is any real number if you are going to consider. So this is going to be exist. This is going to be exist. So automatically we can get to the ontoness is also verified. Then the inverse we have to consider. So f of x is equals to y, we have to replace y. So then by cross multiplication, 3y is equal to this, and from this just I am going to calculate what is x. What is x? X is nothing but f inverse y. F inverse y. So f inverse y is equals to s. So this is the way that we are going to calculate what is the inverse of the given function. Inverse of the given function. Now let us go for the other one. Here a, b are given the functions. Then set a is given and set b is given. Set a is x such that x is a real number and x is greater than or equals to 0. B is a y such that y is a real number and y is greater than or equal to -1. And f of a is given, f of b is given. Verify g is equals to f inverse. G is equals to f inverse. Then just we are going to find out what is g of f, what is f of f, what is a f of f. So g of f of x is, so this we are going to consider. So then g of f of x is g of f of x. What about f of x is f of x is equals to, so it is given as x square. X is a real number which is greater than or equals to 0. So whatever the real number, if I am considering this, if I am taking 1 or okay, f of a is given here. So f of x is equals to, instead of a, we are just taking x. So I am going to get this. So what is g of x is root of, this is root of, and whole square, and next plus 1. So square root of this I am going to cancel, and next I am going to get this one. So which is x square minus 1 under square root, both will get cancelled. Finally I am going to get like this. So it is not x square. G of f of x is root of, this is not there. G of x square, see here, g of x square minus 1 is, x square minus 1 is, this is root of x square minus 1 plus 1. X square minus 1 plus 1. See here some mistake is there. So we have to consider up to here. So this is 1 get cancelled, root of x square, then this will become x. So g of f is equals to the identity mapping. Similarly, f of g of f. So I am just taking f of g of x. So it is f of g of x. What is g of x is equals to root of x minus x plus 1. And what is this? So it is f of x square. So x plus 1 under square root whole square minus 1. So we are going to get x. We are going to get x. So we can say that one is the inverse of the other. One is the inverse of the other. Now g is equals to f inverse. Now we are going to verify the other problem that we have to consider. So here a is equal to b is equal to c, and which is equals to a real number system, and f is from a to b, g is from b to c. So f of x is defined by like this, g of y is defined by like this, and we have to verify this. We have to verify this. So now What is G of F whole inverse we have to calculate? What is F inverse we have to calculate? And G inverse we have to calculate. And of course, F inverse circle G inverse we have to calculate. So, if we are going to prove this, Okay. First of all, we are going to verify what is G of F. What is the G of F inverse of X something else? We are going to calculate it. Now, G of F of X is G of F of X. What is F of X is 3x plus 2. 3x plus 2. What is G of X is 4y. So 4 into this. So I am getting this. 12x plus 8. 12x plus 8. Call this as equation 1. Since f is from A to B, G is from B to C, so G of f is from A to C. It is obvious. A to C. So G of f is from A to B, and next J, this is G is from B to C, then G of f is from A to C. So I am going to consider one element here. That element is equals to x I am taking, and of course another element z I am taking, which is in C. So G of f of x is equals to G of f of x is equals to z. So where x belongs to A and z belongs to C. So I am just considering, and G of f, we are going to consider G of f. See here it is called it as equation 2. What is G of f is given already? 12x plus 8. So G of f is 12x plus 8 I am going to substitute, and which is equals to z. Which is equals to z. See here I am just taking what is G of f of x. This is G of f of x from equation 1. And now here G of f of x is equals to z. So z is equals to 12x plus 8. So now x I am going to get. X I am going to get. So what is x is? X is equals to G of f inverse. G of f inverse z. G of f inverse z. So G of f inverse z is equals to z minus 8 by 12. So this is. Now the another one is, so here it is given already. Now we are going to calculate now what is f inverse and what is g inverse. After that the product. So f inverse we have to calculate. So for that f of x is equals to y. What is f of x is already it is given in the problem itself. This is f of x is equals to 3x plus 2. So I am just taking 3x plus 2 is equal to y. From this, what is x value? What is x value? What is x is nothing but f inverse y. So f inverse y is equal to this. F inverse y is equal to this. Similarly, G is from B to C, and G of y is equals to z, because it is a function, and I am considering one element in B, that element is equals to y. So then definitely that is equal to one element in C, that is G of y is equal to z. So G of y is equal to z. G of y is already given. G of y is equals to 4y. Now just I am taking 4y is equal to z. So from this, what is y? Z by 4. What is y means? G inverse of z. So G inverse of z is equals to z by 4. Z by 4. So what I am going to get? F inverse I am getting, and now G inverse I am getting. F inverse I am getting, and G inverse I am getting. Say this is F inverse and this is G inverse. Now I am just calculating F inverse circle G inverse Z. So this is nothing but F inverse of G inverse Z. What is G inverse Z? It is Z by 4. So this I am going to take it as Z by 4. So F inverse of Z by 4. What is F inverse of y is equals to y minus 2 by 3. So this is Z by 4 by using this minus 2 by 3. after simplifying, we are going to get this. So this is equals to, say this is G of F inverse, G of F inverse. So this is equals to G of F inverse. So from this and the previous result, we can say that equation 5 and 10, we can say that G of F whole inverse is equals to F inverse circle G inverse. So this is the way that we are going to find out. We are going to verify. This is G of F whole inverse is equals to F inverse circle G inverse. Once again, I am going to verify this. Once again, I am going to explain. So first, what is G of F? What is a G of F? So from where, which set to which set it is defined? From A to C it is defining. So I am considering one element in A and the resulting I am going to get in Z. So the image I am going to get in Z. So now G of F is equals to G of F of X. F of X is given and G of X. So F of X is 3x plus 2. G of 3x plus 2 is 4y. So I am just getting 4 into y. So I am going to get this. So now G of F is defined from A to C. I have to consider one element in A. So G of F of X is equal to the image is in C. So I am going to get this. So from this, what is G of F of X is given already. Already we proved that 12x plus 8. 12x plus 8 is equal to Z. So from this I am going to calculate what is X. X is nothing but G of F whole inverse. G of F whole inverse. So now similarly we are going to calculate what is F inverse as well as what is G inverse. So F inverse is F of X is equal to Y. So from this I can calculate X. So X is nothing but F inverse of Y. So F inverse of Y I got. Similarly G inverse of Y. So G inverse of Z, how I am going to calculate? Why I am saying that G inverse of Z? Because Z is the element in C. Z is the element in C. So for showing the differences, I am going to use the variables. And next, G is from B to C. So G of Y is equals to Z. So G of Y is given as 4Y is equals to Z. So Y is equals to G inverse 4Z. G inverse 4Z. Now after that, just a composition of inverse functions. So we are going to get, this is the value, and by using equation 5 and 10, equation 5 and equation 10, so I am going to get finally, this is the result we are going to get. So this is the way that we are going to find some of the invertible functions, and in the next class we are going to continue. We are going to start with the other type of functions. With this, I am going to conclude this. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.